Our next topic to be covered is called standard conditions. The standard state is the state of a material at a defined set of conditions. For instance, of a pure gas, the standard state would be taken at exactly 1 atmosphere of pressure. A pure solid or a pure liquid in its most stable form at exactly 1 atmosphere of pressure. Standard pressure is typically 1 atmosphere. From our gas law units, perhaps you remember other pressures. 760 millimeters of mercury, we called torr, is another standard value. 101.3 kilopascals is another standard value, which happens to be the metric system. Standard pressure is going to be defined as the standard state of any solid, liquid, or gas as its natural condition. Temperature is given as room temperature, 25 degrees Celsius, and the standard state of a solution is taken as 1 molar, 1 mole per liter. Standard enthalpy change is now going to be given just a little symbol to represent that we've been measuring this in a standard state condition, and you'll just see that with a super knot after the H. Defined as the enthalpy change when all reactants and products are in their standard states, running the reaction at standard pressure and temperature of 25 Celsius. The standard enthalpy of formation, given with a sub F after heat of formation, the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. Constituent means just what are those made up from the compound. The constituent elements of carbon dioxide would be carbon and oxygen. Found in the natural state, carbon is written as C, it's a solid. Found in its natural state, oxygen is a diatomic molecule. Forming a compound from its standard state constituent elements is called the heat of formation. Pure elements are not made in nature. That's what we find and build compounds from. If a pure element in its standard state is found in nature, it's just given a value of 0 kilojoules per mole. That's the very definition of heat of formation. We do not form elements, we build compounds from them. Here's a chart that deals with the standard enthalpies of formation. Bromine, for instance, is a liquid at room temperature, and it also is one of the lucky 7 diatomics. Notice it has the value of 0. The natural state of bromine is a liquid in a diatomic form. A single atom of bromine in a gaseous form takes energy to build. We'd have to split this molecule to create the unnatural state of atom bromine. Here's calcium as a solid. That's the way we find it in nature. It has a value of 0. And I see compounds listed, how much energy it takes to build those compounds from the elements it's made of. In nature, carbon is typically found as graphite, which is like pencil lead or a lump of coal, given a value of 0. It definitely takes energy to create diamond, and you can see it has a positive 1.88 value, and so forth. So here's a list in a somewhat alphabetical order of standard enthalpies of formation. I'm going to keep this chart handy. We'll be using it as we do some of our math problem examples. So formation reactions, it simply says reactions of elements in their standard state, the way we find them in nature, to form 1 mole of a pure compound. If you're not sure what the standard state of an element is, we have an appendix in the back of our textbook 2B that has a heat of formations for those pure elements. And again, I happen to have one in front from the previous slide. That one was taken out of our table 6.5. The appendix in the back of your book has a much more extensive list. Because the definition requires 1 mole of a compound be made, the coefficients of the reactants may be fractions. To clarify, suppose I want to build 1 mole of a molecule called carbon monoxide. 1 mole of carbon will react with half a mole of oxygen to create 1 mole of carbon monoxide. So fractions are allowed, simply reading in terms of mole values. The formation of a reaction is the reaction between the elements in the compound, which are carbon and oxygen. But the elements must be in their standard state. We do not find oxygen as an atom in nature. It's too unstable. Instead, we find it as a diatomic gas, and we use the oxygen molecular form to create compounds. And notice what they've done here to keep it balanced, to produce just 1 mole of a molecule of carbon monoxide. We took 1/2 a molecule of oxygen and combined it with carbon in the graphite form. Carbon in its natural state is graphite. The heat of formation is 0. Again, if you're not sure, it's found in our appendix. Oxygen in its standard state is a diatomic molecular gas. It is 0 when it's O2 as a gas, and I don't see it written any other way, so that's my only choice, to write it as O2 as a gas. So what might be some heats of formation reactions for the following? Here's an example. If we wanted to create a formula showing the formation of carbon dioxide gas. Carbon is in the form of graphite, heat of formation of 0. Oxygen is molecular form as a gas, heat of formation of 0. Carbon dioxide as a gas is formed from its constituent elements. And I literally can just simply look up carbon dioxide in its gaseous form, negative 393.5 kilojoules of heat. Delta H would be negative 393.5 kilojoules per mole of CO2 formed. The carbon dioxide value built from its natural state elements. This thermochemical equation is exothermic. Suppose we want to produce aluminum sulfate solid. Aluminum sulfate is actually built of 3 different elements: aluminum, sulfur, and oxygen. Aluminum in its natural state is a solid. Sulfur in its natural state is rhombic. S8 is its natural state. How are we supposed to know that? Well, I check it out using my enthalpy of formation. The standard state, the way we find it in nature, has the 0 assigned to it. And notice it's a rhombic, which is just a geometric pattern of how we find sulfur atoms bonded together. We had diatomic molecules, such as oxygen, fluorine, chlorine, bromine. There were 7 of those. This has 8 atoms bonded together in a rhombic geometric pattern. So this has an assignment of 0. And again, oxygen as an assignment of 0. When the 3 natural state elements combine to form the compound, aluminum sulfate is produced. The fractions here, or coefficients, are simply to create 1 mole of aluminum sulfate. Notice that we're just taking each element individually to build the compound.